Okay, guys, stats section 4.6 goes like this. The multiplication rules for independent events. I believe that we covered a multiplication rule for not independent events. Okay, so here's a rule that we had the last time we took notes. Probability of A and B is equal to the probability of A times the probability of B given A. Okay, now what happens if this condition here that A happened doesn't actually have an effect at all on what this probability would be, right? Like let's say I've got a class and there's 10 guys and there's 10 girls, and I'm going to randomly pick 2 people to give extra credit at the end of the semester. I'm just going to give a whole bunch of points. What's the probability that it's 2 girls, right? Well, the probability that I pick 2 girls would go like this. It's the probability that I pick a girl, which would be 10 out of 20, but then the second part, the conditional probability, there's one less student in the room, so it's not out of 20 this time. And there's one less girl available because we already picked a girl. So the second one would go 9 girls out of 19 students left, and then I would multiply those and I would get my probability. Well, what kind of condition would we have where the second one doesn't really change as a result of the first one? That's what we're talking about here today. So the general multiplication rule is, just wrote it at the top of the page there, probability of A and B is equal to the probability of A times the probability of B given A. Okay, so let's write out the sample space for the following simple, stupid chance process. First thing we're going to do on our very exciting day is we're going to flip a coin. And if that's not thrilling enough, then we're going to roll a die. Big day, guys. Big day. The sample space would go like this. You could get heads and roll a 1, so I'm going to write H1, or heads and 2. So I'm going to write this out 3, 4, 5, and 6. Now those are all the possibilities if heads comes up first. But it's also possible that tails comes up first. So now I've got tails in a 1, tails in a 2, tails in a 3, and a 4, and a 5, and a 6. That's my entire sample space. Can we agree they're all equally likely? There's 12 things here possible. So I'm going to put n equals 12 for the sample size. And if I was writing out a probability distribution, I would write all of these out as an x, and underneath it I'd write p of x, and I'd write 1/12 underneath each one. Okay. Find the probability using the formula above. The probability of heads and 4. That's it right there. That would be the probability using this formula, heads and 4. It would be the probability of heads times the probability of a 4 given that heads came up. Okay. Well, the probability of heads is 1/2. And the probability of getting a 4 given that heads came up. Okay, think about that. If heads came up, these are out. So it's no longer 1/12, it's now out of 6. And the probability I get a 4, once I know this is my scenario, that's going to be 1 out of 6. And 1/2 times 1/6 is 1/12. So, the probability of getting a 4 given that heads came up is 1/6. Now, what's the probability of getting a 4 when you roll a die anyway? There's 6 sides. 4 is one of the sides. It's 1/6. So you see what's happening here. The fact that heads came up has 0 effect on the probability of rolling that 4. Question of the day. Under what circumstances would the probability of B given A just be equal to the probability of B as if A isn't even something I need to worry about? What circumstances would I have where the conditional probability is equal to just the straight up probability because the condition has 0 effect on the actual probability of the second thing happening? Okay, answer. When knowing A happened has no effect, which we just saw with the heads and the 4, on B happening. And so we got a word for that. When the events A and B, flipping a coin and getting heads and rolling a die and getting a 4, are independent. If knowing one of them has no effect on the other one, they are independent. So here's a new formula for you. This is an if. It's a big if. You got to make sure that you read your paragraph and find out if they're independent before you use this formula. If they're independent, the probability of A and B is just simply the probability of A times the probability of B. 1/2 for flipping the coin, 1/6 for rolling a 4 is 1/12. Okay? A couple examples using this idea. I'm driving to school every morning. I only hit one light. It's at 38 and 47. All I want to do is get to Subway and get to school on time. Now, this is outdated because Subway used to be open before school. They used to open at 7, and I would be able to get there at 7 and get a sub, and I'd eat half of it for breakfast and half of it for lunch. They stopped opening, and I'm still mad about it. Now I go to McDonald's. What kind of life is that? Anyway, when I get to the light, obeying all traffic laws, of course, I'm a courteous driver, I have found the probabilities of green, yellow, and red to be independent from day to day, and they are. Here are my probabilities. I've got a 65% chance while I'm on 38 of going right through. I've got a 5% chance of yellow and a 30% chance of red. Find the probability that the light is red tomorrow and then it's green the next day. Well, that's the probability of red and green. And so, since I was told they're independent, this is just the probability of red times the probability of green. I mean, it's really, the formula is really easier today to use. So I just go probability of red is 0.30, the probability of green is 0.65, and I'm just multiplying them together. 0.30 times 0.65 is 0.195. Okay, find the probability of me hitting 5 green lights in a row. Okay, well that's just 2 days in a row. And I had to multiply 2 things. Now I got 5 days in a row. So basically, look, this is going to go find the probability of green and green and green on Wednesday and green on Thursday and green on Friday. Green and green and green and green and green. So that's going to be the probability of green times the probability of green on the second day, times the probability of green on the third day, times the probability of green on the fourth day, and times the probability of green on the fifth day. Now, this is not like earlier when we talked about the probability of the first student being a girl and the second one being a girl, because the first one being picked affects the probability of the second one. Here we're told they're independent from day to day, and so this is just going to go, green is 0.65, and then I could either multiply it out 5 times itself, or I could take it to the 5th power. So I'm going to go to my calculator, and I can either write out 0.65 times itself 5 times like a chump, or I could go 0.65 to the 5th. Save myself a minute. There is a 0.116 as a probability, so there's about a 12% chance that on a given week when driving to school, way back when I used to drive to school and not just walk into my office, that I would get 0.116. Okay? Why don't you guys go to page 304. I'm going to have you read the problem, the space shuttle problem with a disaster. Space shuttle actually blew up. I was in 8th grade. I was home from school that day. I remember it happening because all over the news. Space shuttle went to take off. It was going to have the first teacher, a science teacher, was going to space. And the whole thing blew up. We lost everybody that day. It's going to be similar to this one, except for the tragedy. The only tragedy here is that I don't get to go to Subway if I'm running too late. Read that one, and then we'll have the next video.